In the OT world, I think the word orchestration is not well understood.
This is very exciting. Joining me on the Unsolicited Response Show is John Casey. He is a co-founder and CTO of Cplane.ai. Welcome to the show, John.
Thanks, Dale. Nice to be here and nice to visit with your audience today.
Well, I think it's going to be an interesting show because anytime I can't figure something out, it leaves me with a lot of curiosity. And Cplane.ai recently did a pilot project with ExxonMobil related to the Open Process Automation Forum, OPA Forum.
That's right.
And I was reading it, and I kept thinking I'm not understanding something here. So I wanted to get you on the podcast because, one, I'm a fan of what OPA is doing, and two, I wanted to understand a little bit about this pilot project.
Sure.
We're not going to talk a lot about the mission of OPA here. In the show notes, I'll link to an onstage interview I did with Steve Bitar of ExxonMobil.
Okay,
ExxonMobil is sort of the impetus behind this, and ExxonMobil is looking at it from the standpoint they don't like getting locked into a vendor for 20 or 30 or 40 years. They would rather be able to mix and match, so they created this OPA to, in a sense, create a protocol or a way for various systems to interoperate. And then I understand your company's part of the OPA OPA Forum. Is that correct?
We are a member of the OPA Forum. We've been a member since 2017. We got involved in the vision of Open Process Automation in 2017. And I have since then co-chaired and co-authored the system management specification for OPAF, Open Process Automation Forum. And then I now am the co-chair of the orchestration subcommittee for the Open Process Automation Forum.
Okay. So we're talking about that, and then you had a white paper and a nice video and got some good press, actually, and some really great comments from ExxonMobil on a pilot project you did with them that was demonstrating some orchestration capabilities related to OPA, the protocols and standards and such. So maybe a good place to start is if you could give us just a short overview of what the pilot project was and what it was trying to test. Because when I think of a pilot, I always think we're trying to test something. We don't know whether it works or not. Let's put it in place. Let's see what it works. So what was it and what was it trying to test? That's
a great question. So as you know, or as your readers may read about OPAF, what Open Process Automation Forum is trying to do is bring the best of breed technologies in and to break down the stack of the monolith of existing ICS systems. And therefore, when you start to bring in lots of components, instead of vertically integrated stacks, you start to look at different layers of technology and different vendors and different technology, different layers. You end up with lots of pieces to manage. And so what the pilot was originally intended to do was to basically try to understand how to operate an open process automation system utilizing all this technology, managing all of this stuff over a long life cycle. So, some examples that we tried to do was if there was a failure in the middle of the night of a component, how could we recover from that failure without taking down the plant and without getting somebody out of bed? Can we automate a lot of these manual tasks that you would find through the different life cycles of the plant? And so that was really the goal of the system is determine the art of possible for managing complexity over a long life cycle.
But then when I read the paper, it sounded a little bit different. It sounded like this pilot was primarily focused on the installation process.
That's right.
That you were going to say, we have this system that, and I think I even had a breakdown of it. It was here it says it was simulating a chemical mining and heating process, reactor batch process, heat exchanger, product storage tanks, water chillers. So you had all these different systems. Assuming it's OPA, they were from different vendors that needed to communicate with each other using the protocol.
Right.
And the pilot project was you were going to say, we're going to deploy all these in an expedited manner.
Yeah. And that's a really good point. So in the world of orchestration, you can think of, and we set up different phases for orchestration. The initial setup of the plant, or deployment of the control structures, deployment of the applications, deployment of the different components to make up that chemical process. The second phase would be how do you operate that plant over a long cycle? And the third phase is how do you continually upgrade that plant with either new hardware or new software, security patches, or the like. And so in this first pilot project, we focused in on the first piece, which is how do you initially deploy that that plant and that process. And we'll get into the details of that, but basically, how do you deploy that, and then how do you understand what has been deployed, so you can ensure sort of the next phase and the next phase, which is operate over a long life cycle and then also upgrade.
And I think we should talk about the second and third phase, because in my mind, that's where maybe some of the bigger wins are.
Of course.
In this. And I guess you haven't really talked about what you do here. So this was an appliance or this was some platform that incorporated the networking, the computers, the applications, everything in one. So when you say you were installing this, what were you installing it on?
Yeah, it's a good question. So first of all, maybe just take a second to talk about what is orchestration, and then I'll talk about the components. So orchestration is really the ability to do multiple domains of operation, really reduce complexity of manual tasks, administrative tasks, into a common architecture. So, configuring and updating and managing the network, configuring and updating and managing the devices, the DCSs, the PLCs, if you will, installing the applications on the devices, upgrading and updating those devices, downloading the control block software, determining where that control block software is going. So really taking the, if you will, an IT stack of hardware, operating systems, software applications, networking, security, and putting them in a framework that you can make decisions on to maintain the consistent operation of the plant.
And so as I read this pilot, you essentially took what would have been maybe 14, 15 servers, networking, and all that, and ran it on one platform.
Yeah. So what we did is we set up a pilot plant, right, to essentially to mimic a chemical process. Mm-hmm. We had essentially 14 different DCNs, which is the open OPA word for a DCS, a distributed control system. And we used both a combination of Intel-based chips and ARM-based chips on those DCNs. So we kind of split half and half. We actually distributed the control strategy or the control network across, because of COVID, we ended up placing some of it in New York and some of it in California, just because of the kind of social distancing issues. And so we had essentially 14 different types of computers. And then, so the first step really is to, in detail, discover those devices and put them into a digital twin model, right? So build a digital twin of the infrastructure. So all those computers use different protocols and different discovery mechanisms for understanding the capability of that, I'll call it a topology. right? Comes out of the IT or telecom world. So we build basically a digital twin or a topology of these devices and those capabilities of those devices. So, what I/O each device is connected to, what tags associated with I/O each devices. How do you understanding of essentially the failover policies of those devices, knowing those devices are connected to the same I/O, right? Building a basically digital twin of all the capabilities and behaviors that those devices could play in an open control system.
Now, so this is where I started to get confused because, and again, we're just talking about phase one. We're talking about the installation. The real payoff, if you watch the video, is I think one person said 2 minutes, another person said less than 10. But the idea is installation. You push a button,
that's right,
and it all flows out. To me, I just was wondering how much work was behind that, because you talk about this discovery. Was there a physical system that then you were emulating, or were you building? How were you doing this discovery? I know the I/O, that makes sense. The sensors, the actuators, you get those, right. The tags.
So it sounds like magic. Yeah, it sounds like magic.
How are you discovering?
Sure, that's a good question. So first of all, I'll have to say that this discovery process, this digital twinning, is not a new concept. We've been doing it in telecom world for years. Software-defined networking, network function virtualization, the whole digitization and virtualization of the telecom world we came out of. So this, what you would think in the control system is magic. It's not really magic.
Wait, hold on there. Just stop there for a second. I don't think we think it's magic in the control system when it exists physically.
Yeah, that's right.
Or someone creates a model.
Right.
So we have people that are, I've interviewed some people on here who do a lot of work with digital twins, and they say, yes, we can create a digital twin from a physical instantation. I'm not even going to try to say that word a third time.
Yeah,
they can create a model from something that exists physically, or they can create a very detailed model, which then converts into a digital twin. It just depends what that model is being used for.
Right.
How were you doing it? Were you doing it
right
against something physical or against something that you were creating off, I guess, not in the real world?
No, no, it's actually discovered from each of the devices. So there's certain protocols that are defined in OPAF, Redfish for describing the capabilities and inventory of each of those DCNs and the connectivity of those DCNs to I/O. So essentially, you go and interrogate the networking equipment. You build an understanding of what devices are there. You pull that into your inventory, and we call an inference model. So we build the topology based on physically interrogating every device on the system. So you go from the network switch, then to the different DCNs using different types of protocols. So in some cases, we're using Redfish protocol. Some use agents. There's OPCUA. So we're gathering different protocols together, information from different protocols together, and we're pulling that into a topology model. And I think you use the term model very well, because we actually think of this as building an inference model or a digital twin model inside a database that then describes the behavior and capability of every device through that discovery process. And that the part of that discovery of the data, the metadata around that discovery, is actually defined in the OPAF standard.
So I might have finally gotten it. So are you replacing any of the DCNs with what you did in this pilot, or were you providing the way for the DCNs to communicate with each other in this pilot? Or something else, because that's still what I'm struggling with.
Right. So the DCNs are on a physical network.
Right.
Okay. And we are communicating with those DCNs to understand what capabilities those DCNs have to be able to manage application workloads, right? Mm-hmm. So you want to deploy a set of function blocks onto a DCN. before we deploy those function blocks on that DCN, we need to know what IO it's connected to, how much compute and memory capacity and headroom it has to actually run those control strategies or function blocks. And so what we're doing is we are discovering those devices that exist and putting it into a model, and then making decisions on what to deploy where based on the model of discovery.
So if I've got an existing DCN that has obviously controllers, it has sensors, actuators, it's got some computers at level 2, it's got HMI, operator stations, engineering workstations, historians, maybe a centralized server to manage users and things of that nature. Are you replacing any of that, or are you just communicating with that?
We're just communicating with that. So you just described, right, level 1, level 2, and level 3.
Yeah.
And what we would be doing is we would be automating the management of those 3 layers, right? So deploying function blocks on the DCNs by understanding what actuators and sensors that DCN is connected to. We might deploy an HMI, and manage and update the HMI in level 3, right, in a virtual machine or whatever.
So you would be replacing some of the computers potentially.
When you say replacing, we enable the replacement of them, right?
Right.
But we are actually controlling them. So, for example, in order to run maybe an HMI or if an HMI is running in a virtual machine or a historian is running in a cluster of virtual machines, our software, our orchestration software, would take the requirements of that application, HMI or historian, and we would launch those virtual machines and then install that software on those virtual machines.
Okay, and that's what I thought it was. But then at some point, when you're doing this installation, you had to get those virtual machines and their configuration and all that before could push that button and say, okay, go, and it happens in less than 10 minutes.
Right.
So I guess
so you're missing a piece of the story, right? So first we have to do discovery and understand what compute landscape exists. DCN compute landscape for control applications. At your level 3, what hypervisors and what maybe raw computers, and so we build a topology model of that. The second piece, is what is it that we're going to deploy, and we actually use a technology or a language coming out of the cloud and telecom space called Tosca.
Yeah,
and it's essentially a YAML-based language that describes applications in a very I guess domain-specific way, where you can say this application requires certain capabilities to be deployed, and the orchestrator takes that language definition, and so in that Tosca document that we deploy, we would say, hey, we need an HMI, we need a historian, and we need to deploy 10 different function block groups, groups of function blocks, and where, some hint of where those function blocks would go. The orchestrator reads that definition, matches it up. Basically, this is the requirements to deploy the application. We match it up with the discovered topology, and then we basically do that matching and decide using the requirements and the capabilities of the requirements of the application and the capabilities of the infrastructure. We do that matching and we decide where to deploy things.
Right, but at some place you've defined, hey, this is what an HMI is.
Yes, that's all part of the
application. This is all done ahead of time.
Right. So somewhere when you build out your plans, you'll either generate your Tosca document or you'll describe it in some way. You could either pull it from generate it from an architectural drawing. You could generate it from vendor metadata. but essentially you'll have basically a blueprint of your plans with all the different applications required.
Okay.
Yeah.
Okay, so that makes sense. And to me, I guess I wasn't that impressed with the timing, because we used to do this thing in the control system world. You still see these demonstrations sometimes where someone will show how when they communicate with the controller, they can send it a command to change a setting, turn something on and
Sure.
off. That used
Sure.
to be, hey, I can turn on or off this pump or this light or something. I remember
Right.
seeing those demos back in 2004.
Right.
And a lot of people are like, of course, you can you can use a control protocol to control something. This
Sure.
is
That's right.
obvious, but of course the implication was there was no security attached to it, and this was a problem.
That's right.
So I sort of had the same sort of feeling that if you do all this work up front to understand the system, to define the system, to get it all in these languages you're talking about, when you push the button, it will install very quickly. Most of
Yes.
your work was done on the front end, not after that button was pushed.
Sure.
So
That's right.
I guess if you had highly repetitive plants, there's some advantages that you wouldn't have to define it every time. You'd gain a lot of efficiencies after manual install or something like that. But to me, the real win is possibly in this stage 2 or stage 3.
That's right.
So once someone has this installed, what are some of the benefits in terms of maintenance, upgrades, things of that nature over let's say just a normal virtual system or a physical,
Sure.
actually on servers? What are some of the benefits?
And that's a great question, and actually that's the point. To install something is relatively easy, right? To do it in a way where you understand its life cycle operations and its requirements over a long cycle is really the key. And so the whole idea of getting all this stuff digitized, getting the applications digitized, is to maintain consistency and availability of the plant over a long life cycle. So being able to take action on some sort of event, maybe it's a security event, maybe you find that a device had been compromised. You can now make good decisions to keep the plant running by, I'll just give an example, maybe black holing that device, keeping it running and putting it into a honeypot. And then moving that workload that was on that device, spinning up a new instance of that control logic, and ensuring that the plant is continually running through that security event. If there's a security patch that needs to be done, being able to apply that patch by maybe moving workloads around without taking the control system down, right? Mm-hmm. Or doing it in a way where you're reducing the time of maintenance windows, for example.
And I guess, how would you compare what you're doing here to something that someone might get if they deployed Nutanix? Because we've seen that quite a bit in the space, where it's a platform that everything's virtualized, the network's virtualized, the servers, the workstations are virtualized. Is this just an extension of that concept, or is it something different than that?
It's in the OT world, I think the word orchestration is not well understood. In the IT world, the pace of change is so great that we actually have created lots of definitions for orchestration. They all sort of mean the same thing. Nutanix, VMware, OpenStack, Kubernetes, they all have their methods of orchestration, but they're orchestrating a very small, component, right? So Nutanix basically is looking after Nutanix boxes. The hyper-converged Nutanix. So you're deploying, workloads on that Nutanix box. Mm-hmm. What we're doing is something called system orchestration, where we're looking over the entire life cycle of the plant, all the way from level 1 all the way to level 3. And you might have a Nutanix box that we also need to orchestrate, but Nutanix is really going to orchestrate its own thing. So by putting it in a larger system approach, we can take the commands. For example, if we need to spin up a new VM or we need to, create some storage, by understanding that maybe this DCN needs some state management, we could then send that command to Nutanix. Nutanix will do its thing, but we're the overarching orchestrator of a plant.
Is this orchestration going down to level 1? So are you, like, I know the I/O is probably the last thing that's ever going to be virtualized or dealt with in this manner. Your sensors, your actuators, you're going to need that I/O to those. But I could imagine, and we've even seen, like Emerson has some virtualized DCS controllers. Are you starting to see that being absorbed into this platform and orchestration?
For sure, yeah, for sure. So we are really talking at level 1. The DCSs that we deployed in the pilot, we're running Schneider Electric's 1499 language, and so by understanding the I/O that particular DCN was connected to, we didn't automate the tags, although we could have. By looking at the requirements of the application, we were to deploy containers essentially on the DCSs itself that ran that control structure.
Oh, very cool. Very cool. Yeah, I really think that's the future. It's something that
That's right.
A lot of people have a hard time getting their head around, but all the advantages you get of virtualizing the servers and the workstations are
Right.
there. The only hard part is that I/O. Just one other question.
I will say,
Go ahead.
I mean, that's also one of the advantages of moving to an open control system, right? Is that, you can take advantages of Moore's law. Maybe the current DCS is CPUs, right? I mean, go back to 20 some years ago, right? If you if you can take advantage of the current CPUs, you can move things like you can run multiple maybe control loops on one DCN. You can bring your model predictive controller AI down to the last inch, right? Basically down to that DCS. And so, your processing cycle is a lot faster, and the proximity to the processing you're doing is closer to the actuators and sensors.
Yeah, and from a security standpoint, we had some good talks on this at S420. You get a lot of those DevOps benefits that are really security related, those die benefits that you can just kill things, bring them up, bring them down. It's hard for people to maintain persistence. And at level 1, that's one of the biggest challenges we have in this space is those level 1 devices live on for literally decades, 2-3 decades. They're the hardest thing to get people to change. So if we can just make that real easy to change, we can deal with security issues.
That's right.
I just one last question on this, because we kind of veered away from it. On the OPA side of things, so you did this demo along with ExxonMobil, this pilot project. Did it prove out anything from an OPA perspective that was important?
Yes, it did. In fact, what we proved is that essentially a open control system can be managed, deployed and managed through its life cycle, essentially, without bringing a bunch of IT DevOps people into the mix, right? That you can do it, that you can manage these systems with your existing skill sets in the plant, right? You don't have to bring it, they're not going to have to learn, Linux and, shell scripting and, all the various IT technologies that we're bringing into the open control system, that essentially you can bring existing, or, you can use your existing skills and make that technology innovation transparent to your plant.
Well, there's going to need to be some people to work with your solution or a similar solution, right? And those people are going to need those.
Yeah, but they're not going to need it. Sure, of course. I mean, there's going to be a little bit of any sort of knowledge transfer, but you're not going to need to have people who are that in depth in Linux and all the various tooling coming from IT. is that it's going to be at a different level.
Okay. Well, that might be another rabbit hole. I wanted to ask you one other question, though, rather than dive down that one. And that is related to, you had a blog entry on your site that was talking about the industrial edge. And it made a strong contention here. First of all, when you said on, well, you didn't actually write this article, but the gentleman who wrote it said the industrial edge equals on-prem computing. And I think that's accurate. I think when most people are talking about industrial edge, they're talking about the edge of what the asset owner has control of, not the cloud.
That's right.
But then the idea of how much will be run on the industrial edge and inside on-prem and how much is run on the cloud is really where I think the decision is made. And there was a lot of talk about how for this world it needs to run on-prem. It needs to run on the industrial edge or inside. And my question on this is that somewhat related to the industries you're looking at? Because I could see if you're talking about a DCS in a refinery with very tight performance characteristics, that might be required. But if I'm thinking like a water system or a pipeline or something like that, where they're used to things being delayed minutes and can probably live sometimes even with hours without communication, it wouldn't be an issue. So I get the question, I guess, to put it in the
yeah, I mean, it's a good
is it related
question.
To performance requirements, or
well,
it's
related to proximity of and access to data and essentially speed of light, right? If you have to make quick decisions, under a second, then you want to place your your processing as close to that point of actuators and sensors as possible, right? If you're talking about making decisions in hours, as you say, right, then you can move that processing, right? This is principles of distributed computing, right? The requirements of the application really will force you into, or give you choices essentially to place the processing close to your actuating sensors or in the cloud. And I think there's some things that lend itself really well to the cloud. But if you have to make decisions on under a second, if you have to make if you have to keep something running, then you should place it in your plant close to your actuator and sensors.
Well, and then there was another thing, and this one is maybe a little more interesting in terms of, because I think we would agree with that, but there's going to be a lot of things that aren't time sensitive. For example, scheduling, or recipes, or for manufacturing, or again, some leak detection systems for pipelines. I mean, they need to hear from them every couple of hours, so that if they lose minutes of data, it's no big deal.
Right.
But then there was a talk about where the data, and they said, there was a quote in the article, endlessly paying cloud operators ever-increasing fees for data storage is untenable for industrial companies.
Okay, I didn't want to go there, but
that seems strange to me, because I think the TCO, the total cost of ownership of keeping all that data locally and trying to process it locally, I would think for almost any big data application, that just seems to fly in the face what I'm hearing from other people.
Yeah, right. So you're talking about business dynamics now, right, as opposed to technical architectures. Right. So look, there are lots of articles written. There's lots of data out there about the economies of scale that you get with the cloud versus your own sort of private cloud, right, or whatever you want to call it, right? And so I'm not going to repeat that. It's very well understood. There's white papers and stuff. But I do think that what you get in the cloud is simplicity and abundancy, right? So if you want to do some analytics and you want to do it over the course of a month, and you have terabytes and even petabytes of data, you have that capacity, right? To build your own data center, to have that sort of short-term capacity is very difficult and very costly. And so I think, from a business economic standpoint, you need to decide, are you placing all your data in the cloud and paying for it just because it's convenient, and you're not really utilizing in short term, but it's a long-term strategy? It's probably not very economical. You could probably buy, your SSDs and your, Ceph storage and all of your technology and develop that for long-term basis a lot cheaper internally. But if you're going to, bring some, do some projects, some research projects on analytics for short term, that's a very, very good reason to use the cloud.
Sounds like, though, that's not the mainstream point of view at this point. I hear most of my asset owner clients are basically moving as much as they can, as fast as they can, just because they don't want to deal with it in-house. They don't want the people, they don't want the equipment, they don't want the space, they don't want the responsibility.
I think we're a lot further along in that buying cycle in the IT industry. So what you'll find in the IT industry is the initial reaction in the IT industry is to move everything to the cloud, and then they realize that they're looking at their expenses and they're like, well, we could, so some of those projects could probably move internal and we could save costs. Some of those projects stay in the cloud because they're to shorter distance. So I think in the IT industry, probably a lot more thinking goes on around that than maybe what's currently going in the ICS world. But I think it's a maturation.
No, I'm absolutely sure you're right about that. And I also know we're seeing people moving all data to the cloud. They just, and a lot of data sitting in the cloud, not doing anything, just waiting for a project.
Empty data lakes, right? You're paying a lot of money for. I would say that, from a business perspective, if you're passing that data on to or passing that cost on to somebody else, it's probably not part of your equation of whether or not you should, move it locally. A lot of the cloud services, right, are, you're just passing that cost on to the consumer.
Okay, well, let's end on just a very open-ended question, because as you can tell, I've kind of groping through this interview, trying to understand it. You're right, orchestration is not a term we use much in OT. When we hear it, mostly we think of it in terms of a SOAR product. So that's security right. Orchestration is that's the terminology we hear. There's very little orchestration going on in a lot of asset owners. There's still, we even see backups where people pull out media to restore computers. So you're talking about almost level 0 orchestration at that point.
Sure.
So maybe the open-ended question is, what should the OT world understand about either the project or orchestration that I haven't asked you about? Or is there like a key point or a key learning that we haven't talked about?
It's a good question. I mean, I think that orchestration in an open control system sets you up for providing a more secure, easier, more highly available, and more dynamic environment, right? And so whether you take the security angle and being able to react to security events dynamically, whether you want to easily provide high availability of systems or easily be able to upgrade different processors and different technologies over time, the orchestrator looking over that application landscaping, looking over the hardware landscape and the capabilities, and being able to easily deploy and manage those workloads onto your your compute landscape is a big advantage. And so either reducing or eliminating some of the manual operations in your plants, from maybe network orchestration, security orchestration, updating systems and keeping them up to date, and even moving workloads around and maybe reprioritizing what's running, whether it's continuous or batch process. Redeploying your maybe different configurations for your batch process.
Okay, well, we'll have to dig into that some more. I do appreciate you coming on. I will say that certainly the ability to update systems, change systems, rebuild systems, redeploy systems is something that is looked at with great fear in a lot of our asset owners in this space. That's why it's basically install, don't touch, put it in run to fail maintenance mode.
That's right.
And that with all the challenges and problems related to that sort of mindset. So this sounds like an extreme way, kind of the opposite end of that run to fail. It's actually,
well, I will say it's been proven. It's been proven in the telecom space. It's been proven in the IT space. And so, as you start to get more out of your ICS systems, be able to place more analytics and AI and model predictive control at the edge. These systems will help you.
Okay. Well, keep us posted. I'd be very curious when the case studies come out and such to see where this is working and how it's doing. But I just want to thank you, John, for coming on the show.
Thank you, Dale.
Well, that's the show. I want to thank my guest, John Casey. He's the CTO and co-founder of Cplane.ai. You can get more information on this pilot project they did with ExxonMobil. As I mentioned, they have a nice video on it with ExxonMobil giving their thoughts. There's a white paper. There's more detail. Encourage you to look at it, and we'll be tracking this project as well as other things at the OPA. It's a very interesting project. I'd like to hear who you'd like to see on the show. So you can email me at s4@digitalbond.com, any ideas you have about guests or topics, or you can even suggest yourself. And we do like to have questions. We include those at the end of these shows. You can record your question. Go to dale-peterson.com. On the right-hand side, you'll see record your question. Simply click on that and speak into your mic. And I'll talk to you next time. Something warrants an unsolicited response.